Okay, so in this lecture, we are going to talk about a data structure called heaps. All right, so heaps are going to be a very important data structure. Okay, and we are going to talk about what is a heap. We are going to talk about operations on a heap. Okay, and finally do some complexity analysis. Okay, so this lecture is also going to overlap with certain aspects of heap that are also going to be taught in 2270, your data structures class, which hopefully you're taking at the same time. All right, so we are going to focus more on the properties, the mathematical properties, the complexity, the computational complexity, deriving complexity results, and so on. How to program a heap, how to use a heap, when to use a heap versus other data structures will also be covered in 2270. We are not going to go into it in as much detail here. Okay, so what is a heap? All right, so heap is a data structure, and in your data structures class, you would have learned about the concept of an abstract data type. Okay, so what is an abstract data type for a heap look like? Well, abstract data type for a heap looks like this. So you're going to have an array A. Okay, so a heap is going to have an array A of numbers, and these numbers are going to be called the keys. Okay, so it's going to be an array of numbers. Okay, 0, 1, and so on. Those are going to be the numbers in the array, and these numbers have a special name. They're going to be called the keys. All right, and you can also have like other data. You can also have other data. Okay, so we are not going to talk about the other data, and typically sometimes this is called the payload. We are not going to talk about this. So as far as we are concerned, a heap is just an array of numbers. All right, the operations. Okay, the operations are going to be heapify. Okay, so given an array A, convert it into a heap. Okay, what is a heap? Well, a heap, I said, is an array, but now let me say it is a special array with some special properties. Okay, what are these special properties? Coming right up. All right, so it's going to be a special array with special properties, and heapify is going to take an ordinary array and make it into a heap. All right, what else? So we need an operation to insert an element into a heap. Okay, and here when I insert an element, I'm just going to be worried about inserting a number or inserting a key. I'm not going to be worried about inserting other stuff. Okay, that will be taken care of in your data structures class. Likewise, delete. Okay, delete a key. All right, or typically you can have delete a key or delete an index. We'll talk about that later. And then the minimum element, which is find the smallest key in the heap. All right, so this is going to be something like the abstract data type. Right now, a heap is just going to be an array of numbers called keys. We are going to talk about more things like how do we make a heap out of strings, or how do you make a heap out of your classes, and so on. All right, so let me talk about what special thing about a heap. It's called the heap property. Okay, all right, so there are two types of heap properties. One is called the min heap and max heap. Okay, and we are going to focus mostly on min heaps, though everything we'll talk about min heaps. With max heap, it's very, very simple. You just reverse the direction of the inequalities. You will know in a second. So I will reserve max heap for later. Right now I'm going to talk about min heaps. I'll tell you how to remember and tell the two apart. Okay, as I mentioned earlier, a heap is just an array. What is this array? So here is an example. Let's say here is the array 2, 4, 5, 7, 6, 18, 6, 14, 9. Okay, so it's not a sorted array. So the elements are not in increasing order, and this is A of 1, A of 2, A of 3, 4, 5, 6, 7, 8. Okay, so this has 9 elements in the array. Alright, so here is the thing. Every element, if I have element number 1, then element number 2 is called the left child, and element number 3 is called the right child. Okay. Likewise, for element 2, element number 4 is called the left child, and element number 5 is called the right child. In general, if you have element number I, then 2i is the left child, and 2i plus 1 is called the right child. All right, and likewise, just like 2i is the child, the reverse relation is called the parent. So I is the parent of the elements at 2i and 2i plus 1. So for example, let me take the element at 4. The left child is going to be 8, and the right child is going to be the element at 9, okay, which is itself a 9. How about the element here at 6? Well, 6 has no left child and no right child. Okay, so if the element 2i or 2i plus 1 does not exist in the heap, then you say there are no left child or no right child. If it does exist, then you say it has a left child. If 2i exists, if 2i plus 1 exists in the array, then you say it has a left child and a right child. Likewise, for a parent, if you have element 2i plus 1, the parent is given by I. And this is simply divide by 2 and round down. Okay, it's divide by 2. So for element j, the parent is j divided by 2, okay, is the parent. And this is the floor notation. It's taking the fractional number and rounding it down if it's a fraction. If it's not a fraction, it's the same value. So this is the parent relation. And element a of 1 has no parent, and it's called the root. All right. So with this in mind, a heap is just going to be visualized better as a tree. So for example, if I took this heap and I put 2 at the root, its left child is a 4, its right child is a 5, 4's left child is a 7, 4's right child is a 6, 5's left child is an 18. You see, you're just writing out the elements of the array in this order. 6. 7's left child is going to be a 14 and a 9. So a heap is also a special binary tree. Okay, so it's a tree. You can think of it as a tree laid out as an array. That's what it is. Okay, so it's a tree that's also laid out as an array. All right, so what is special about this tree? Well, every node has at most 2 children, right? Every node has at most 2 children. Now it has a left child and a right child, left child and a right child, left child and a right child. Okay, so one key property that distinguishes it from a binary tree, let me write it here. If a node has a right child, it must have a left child. Okay, so if a node has a right child, it must also have a left child. Why? Can you think about it in terms of an array and convince me why is this true? If a node has a right child, then it must also have a left child. Can you think about it? Okay, so if you paused the video and thought about it, hopefully, if not, take a few seconds. Here is a hint. Think of any node is basically also existing in the array, right? A heap is just an array. The tree is just a way of visualizing the heap, right? So if you have a node, this node must be at a position I. So the node must be at a position I, or A of I. All right. If it has a right child, then 2i plus 1 is a valid location in the array. Okay, so the array has a location and label 2i plus 1. Well, if it has 2i plus 1, it must have 2i. Okay, because an array is just a straight line list of numbers, right? So if there is a 2i plus 1th element, there must be a 2ith element, right? And therefore, if there is a right child, there must be a left child. All right, so this is a very, very simple property of a heap, but it kind of guides us, gives us some intuition about what heaps look like. All right, where are we so far? Heaps are arrays. Okay, so let me summarize. Heaps are arrays. Number one. Number two, for every a of I, a of 2i is the left child if 2i is less than or equal to n, where n is the size of array. A of 2i plus 1 is the right child if 2i plus 1 less than or equal to n. If 2i plus 1 were greater than n, then there is no right child. If 2i were greater than n, then there is no left child. All right, so this is what we know about a heap. Now is the all-important property. And we will call this the min heap property. And it's really simple. Min heap property says that every node a of I is less than or equal to a of 2i, and a of I is less than or equal to a of 2i plus 1 if 2i less than or equal to n, if 2i plus 1 less than or equal to n. In tree terms, at every node, the value of the node is going to be less than or equal to the value of its children. So if a node is at 7, then its children could be like 8 and 7. Or if a node is 5, then its children could be 15 and 12. Okay, or it could be 12 and 15. Doesn't matter. But remember, the value of a node must be, of a parent, must be less than or equal to the value of the children. And this is called the min heap property. Now, if it were just the other way around, value of a node is always greater than or equal to the value of its children, that's called the max heap property. All right, let us just work with min heap. The max heap property is just the opposite. Change this less than to a greater than equal to, and that becomes the max heap property. All right, so this is the min heap property. So let us give some examples of heaps and check that they have min heap property. Okay, so here's an example of a heap. Okay, remember a heap is an array. So this is the array. Okay, so let me write on the positions. All right, so 2 is at the root, and then 5 and 4 are its children. The children of 5 are the elements at the 4th and 5th position, which are 7 and 8. The children of 4 are the elements at the 6th and 7th position, which are 12 and 7. And the 4 only has a left child, no right child, which is the element at position A. So this is how the heap is laid out as a tree. All right, verify that this satisfies the min heap property. So 2 is less than equal to 5, 2 is less than equal to 4, less than equal to, less than equal to, less than equal to, less than equal to, less than equal to. So every parent is less than or equal to its children. So therefore, this is indeed a heap. Okay, so let's do one more example. Okay, so here's the next example. Here's the array, and here is the tree. Okay, make sure that the tree is correctly reflecting the heap in the array. All right, let's check the min heap property. So 2 is less than equal to 9, 2 is less than equal to 18, 9 is less than equal to 9, so they can be the same. Remember, the parent and the child can be the same because it's less than or equal to, remember, 9 is less than equal to 15, 18 is less than equal to 19, but here is the violation. See, so this is wrong. So 14 is in the wrong place because its parent, which is here, okay, 7 divided by 2, the floor, which is 3, so the element at position 3, so 18 is not less than equal to 14, therefore not a min heap. All right, now let's do an example of a max heap. Okay, so here is an example of a max heap. Okay, so here is an example of a max heap. So in a max heap, the parent is greater than or equal to children, whereas in a min heap it was just the other way around. So here 17 is greater than or equal to 11, so 17 is greater than or equal to 10, 11 is greater than or equal to 10, 11 is greater than equal to 9, 10 is greater than equal to 2, 10 is greater than equal to 8, 10 is greater than equal to minus 1, 10 is greater than, 1, 10 is greater than equal to minus 2. All right, so this is indeed a max heap. Just to give you an example. All right, why are we so interested in a heap? What is the primary reason we are interested in a heap? Okay, here is the basic result. If A is a heap, if A is specifically a min heap, then the very first element, A of 1, the root, is the minimum element of A. This is really, really simple. So let's take an example. Okay, so let's take the heap. Okay, 2, 3, 5, 7, 4, 9, 5. Okay, so you can see the smallest element is always at the root, or the smallest element is always the very first element of the heap. Why is this? Okay, so let us prove this result. All right, what's the proof? So proof is going to be by induction on the depth of the heap. What is the depth of the heap? The depth of the heap is the maximum number of levels where the root is considered level 1, the second level is considered the children of the root, the third level is considered the children of the root, and so on. So let us do induction on the depth of the heap. Okay, so base case, heap depth equals 1. If heap depth is 1, then the heap is very simple. It's simply an array of size 1. It's just got one element in it. Okay, so it's just the root by itself. Therefore, root or A of 1 is trivially the smallest element. What is the induction hypothesis? Well, the induction hypothesis says that let the result, what is the result? that the root is the smallest element, that the root a of 1 is the smallest element of the heap. Result hold for all heaps of depth d. All right. So if the result holds for all heaps of depth up to d, okay, so we are going to do strong induction. So depth less than or equal to d. Let us say the result holds for all for all heaps up for depth less than or equal to d. Then prove it for heaps of depth d plus 1. How do we prove this for a heap of depth d plus 1? Let's look at a heap of depth d plus 1. It has a root, all right, and then it's going to have a left child, and it's going to have a right child, and it's going to have a subtree underneath it, another subtree underneath it, and the entire depth is d plus 1. Therefore, each of these subtrees has to be of depth less than equal to d. Okay, and if you look at the subtree by itself, if you forget everything else, if you look at each subtree by itself, each subtree is a heap. By itself, right? It's a subheap, if you will. All right. So if it's a heap by itself, then if you take the element of the left subtree, let's call this L, and let's call the element of the right subtree U. I already used R for the root. Okay, sorry about that. So then L is the minimum element of left subtree. Likewise, U is the minimum of the right subtree. And this is by induction hypothesis. Because of the induction hypothesis, because the left subtree and right subtree are smaller trees, this is true. And therefore, R is less than equal to L and R is less than equal to U. Why is this? Because of min-heap property. Because of min-heap property. Now combining the two, well, L is already the smallest in the left, U is already the smallest in the right, and R is smaller than L and U. Therefore, R is the smallest element of the heap. QED. So this is how the induction proof goes. All right. So what have we proved? We proved that because of the min-heap property, the element of the top has to be the smallest. Okay, or in the array sense, the element at the very first position has to be the smallest. All right, so now that we have defined heaps and we have defined heap operation, we have defined heap properties, we are now ready in the next video to define what are heap operations. Okay, so now that we have defined heap properties, we are ready in the next video to define heap operations. See you there. Bye.